we were examining the second order circuits. What we have done up to now, we said what it is, and then we find out the state equation representing the second order circuit. That's a mathematical model. So we have seen how we get the state equation, and we have done it for this example. Parallel RLC circuit, the corresponding mathematical model, which is a second order ordinary differential equation. How we found it, we explained that. Now the next step is find the mathematical solutions. Solution, not solutions, of course, it's just one solution. So to find this mathematical solution, we try to remember what you have done in differential equation course. So to find the mathematical solution, we've got to calculate two things. One of them, the homogeneous solution, which have examined already, that homogeneous solution. Now we will be examining the particular solution. Once we found the particular solution, then we're going to add this solution to the homogeneous solution to get the general solution. So this video is related with this frame now. So let's go back now to the open board. Here is our circuit. So this is the differential equation which models this second order circuit. Homogeneous solution, we said we already calculated it. Now we will be calculating the particular solution. Let's write it, particular solution. So particular solution, what it is the source type function. Source type function. When it is substituted for this variable in this differential equation, left hand side should be equal to the right hand side, since it is a solution. So that means we already know that the type of sources could be either independent sources, independent sources. We have already seen those. Just remind you what they were. So it could be either independent current source or independent voltage source. In our case, it is an independent current source. So the type of this source could be either a DC source or an AC source. So that means if IT is an AC source, then solution, particular solution, let's say XT particular, is going to be in this format, A cos omega t plus phi. So this is not IT, that is the particular solution that we are going to calculate. So if this is a cosinus type, let's make it like that, A cosinus omega t plus theta. So this is a sinusoidal function. If this is a sinusoidal like that, so our particular solution is going to be in the same form. When we say it in the same form, this is particular, this is sinusoidal as well. And we already know that the frequency, source frequency, and the particular solution sinusoidal function's frequency is going to be the same. It is not changing. Why it is not changing? Maybe it is easy to explain that. Because we are getting the derivative of the sinusoidal function. Derivative of a sinusoidal function is another sinusoidal function, and this sinusoidal function frequency is the same as the before the derivation is taken in. So that means a sinusoidal function, derivative function's frequency does not change. So the omega is not changing. What is left? So this is known, and we will be calculating this. When I said this, because this is xt, that means there are two variables here. One of them state variables that we need to calculate for the particular solution for this variable. That is VCT and ILT. So for each variable there are two parameters. So if we consider two of them, so we're going to calculate 4 parameters. So it is a bit boring. We have done it for the first order circuit. We are not going to examine this one at this moment. The reason, later on you're going to see that in circuit analysis course, how we can calculate this particular solution if the source is AC source. It is a new domain which is called frequency domain. We will be doing it in a very short way. That's why we are not going to go in details for that AC case. So for DC case we will be examining the situation. How we are going to examine it? We are saying, by definition, I know that it's going to source type. So if it is IT, is independent current source, is a constant. Let's say it is capital A. It could be 5 volt, 6 volt, 10 volt, whatever it is. So we are saying particular solution now, VC particular, is going to be in the same form. Then I consider D. I didn't use B. I could use B. I use D. And IL particular E. So these D and E are the parameters that I am going to calculate. All I know is this particular solution is going to be in the same form of the independent current source form, which is DC. So how I am going to calculate those is easy, because these estimations, since they are solution, I would put these values or substitute these values in the differential equation, substitute for these values in the differential equation. Left hand side must be equal to right hand side. So if I consider the left hand side of this differential equation, derivative of those two is going to be 0, 0, because derivative of a constant is equal to 0. And keep this as it is, minus 1 over RC, minus 1 over C, maybe that is a bit better, 1 over L, 0, and VC particular D, EL particular E. So that's D and E, plus 1 over C, 0. IT, our estimation. Now I'm not going to examine, as I said here. Don't consider this one. We are not examining this one, we said. We are examining this one. So IT is a DC sort and value is A, so I put A here. So this gives us two unknowns, two equations. So we can calculate D and E from this. So let me write these equations here. 0 is equal minus 1 over RCD minus 1 over CE plus 1 over CA. The second one, 0 is equal 1 over LD, and E times 0 gives you 0. That is 0 times A gives you 0, so plus 0. So from this one, we can say that D is equal 0, isn't it? That's 0, so D equals 0. Why it isn't? Y over L is a constant and different from 0, so you could take this out. When D equal to 0, so that means this term is 0, and if you multiply that with C, from this you can find out E is equal A. So I said I was going to calculate those two, which are the particular solution, and I found those two. So we're finished. This is the particular solutions. A is known as an independent source current source value. So that is how you can calculate the particular solution in differential equation course, as you have done it in differential equation course. But in here I would like to show you an alternative to this, considering the physical world. How we are going to consider the physical world? We will be considering the definition relation of the capacitor, which is IC is C times dVc over dt, and inductor definition relation L dIL over dt. As we said, the particular solution is the solution in the form of independent source. So Vc particular solution is going to be a constant. So that constant. So when you take the derivative of it, then derivative of a constant is 0. So IC is equal to 0. So IC is equal to 0. That means open circuit. For this one, since IL, this is IL, is going to be a constant in the form of independent source. So if it is constant, so derivative of this constant is going to be 0. From that, I can say that VL, that means inductor voltage, is equal to 0. That is short circuit. Circuit. So we already calculated that IC and VL is 0. So what about that VC? So that VC, we don't know that VC. And we don't know IL. Need that D calculation. But since we've got open circuit and short circuit elements in our circuit, so I can change this circuit now. Let me drop this down. When you say that in capacitor current is equal to 0 open circuit, that means let's make it red color. So it is open circuit, so move that out. And then inductor voltage equal to 0 short circuit, that means this is going to be short circuit. You're going to make it like that. So since this resistor is connected to the inductor in parallel, so the voltage of inductor is also the same as the resistor voltage. If you consider the resistor definition relation, so VR equal to 0, R is different from 0, so IR equal to 0. If both of them 0, we already explained that, we're going to consider this is open circuit. So in this case, this is open, this is open. That means the current passing through the inductor is going to be the same as this, isn't it? So that's open circuit, that's open circuit. Kirchhoff voltage law equation for this node gives you that IL equal to IT. So that means IL particular equal to IT. IT is A, DC source current. What about VC? Since the voltage of the inductor equal to 0, we already found that, this capacitor is connected to that inductor in parallel. So voltage of this capacitor must be equal to this inductor voltage, and then VC is equal to 0, isn't it? Because VL 0. So what we found here is the same as this, isn't it? Conclusion is this. If you are looking for the particular solution in a circuit where the independent sources are DC, you can directly use this circuit and calculate the element currents and voltages, which are the particular solution. How we are going to do it? You're going to make the open circuit all the capacitors, and you're going to make all the inductors short circuit. So this is not only 3 or 4 second order circuit. Any circuit which includes capacitor and inductors in it and independent DC source, you can apply this rule. So there would be no problem. So that is the end of this video now. So let's stop here.